So for the sake of the video, there was a question asked about what exactly is flatten for. And so flatten really is just how you're processing the information. Because all the information is there, right? We have a list of 70 points on this grid. And if it's not flattened, we still have a list of 70 points. Except now when it's not flattened, it comes through as a package, little mini packages of information that are grouped together. Now, when we start building things off of that, you'll understand why it's very important. Because particularly, we're going to move into solids now and surfaces. But when I build a surface on the grid, it has a very different behavior for how those points are actually calculated. Does that make sense? You don't want redundant information. Okay. Oh, another important thing to say is when you're mapping geometry into cells, particularly, or any kind of subdivided surface, it's important to understand the relationship of one point in a group to the same point in another group. So that's why you would need this. So if I wanted, say, every single one of these grid cells to map from its origin point here to the fourth cell's origin point, then it would, or rather, fourth cell and one up, right? You'd be able to grab this one here, which is the 0 point for that cell, and then you'd be able to map it to the 0 point of this cell. But you need to have it in a set in order to do that. Does that make sense?
So is it become easier?
Yeah, it can be, yeah. But it all depends on what you're trying to do. Okay, so so let's start looking at solids and what really changes here. So what I was talking about with how it actually calculates the whole cell is really going to get important here. So let me just kind of delete that. I'll disconnect this, but I'm going to use it again later to show you more. But this is where I'd like you guys to kind of follow along, right? So the cool thing about cells is that while it technically does not have a surface within it, it does have curves or edges, or more importantly, a boundary within which you can apply particular processes. So if I wanted to create surfaces on each one of these cells, all I have to do is go to surface and then freeform. I think the easiest way is boundary surfaces. I think so. I might have to deconstruct. But anyway, let's try this one. Surf freeform. So this is under surfaces and freeform. And that should create surfaces. All right, so now let's take a look at the input. And so typically if I'm trying to troubleshoot the information, along the whole trail, right, of information as it's flowing through, I check my, I usually work backwards. You'll see me do that later on, but check your input and your output. Because, one or the other, like something happens in here that changes information almost all the time. So make sure that you're always checking your input and your output to understand what's happening. So we have 54 cells. Let me go back to an easier to manage number here. So I'll do 3 and 3. All right, so we have now 9 cells that are being fed into the boundary surface, and then it gets processed into individual surfaces, and we still have 9 cells. This one in particular doesn't change the list at all. It just converts all that information into any eligible surface. So we have 9 of them. If you plug this in to a panel, you'll see that you've got 3 packages of 3 surfaces. So, so I mentioned to you before that Grasshopper is a cyclical process of constructing geometry, deconstructing geometry, and reconstructing it into something else. So this is the point at which we're going to deconstruct the geometry and then analyze what its behavior is. So if I want to be able to use each of these surfaces individually, I can at this point because I have those 9 surfaces. But what gets really, really powerful is when you go up to surface and analysis, there's this one that's called Deconstruct BREP. And did Jeff explain BREP to you yet? Okay. So the terminology of solids and BREP are similar, but they're not identical. A BREP is what's called a boundary representation, which is different than a solid because it doesn't necessarily have any inherent solidity or void within it. It's just a boundary. So it's a mathematical determination of volume. That's it. So surfaces can sometimes behave as BREPs. I would say a BREP cannot always be translated back into a surface. I think I have that right. But for the most part, for our purposes, they're going to be pretty easy to slide in and out of, back and forth across the two. So anyway, deconstruct BREP. So these surfaces really, I made notice how the command is called boundary, and it created surfaces. So a boundary representation is essentially, in this case, the same as a surface. So when we drop deconstruct BREP in, this is under surface analysis. Now you notice it looks a little bit different. So it's asking for a BREP. We gave it a list of surfaces which are going to behave like BREPs in this particular case. And the output that it's given us, let's hover over that. This is a term I'm going to use often too. We are deconstructing a BREP into its constituent parts. So that's important to understand because if you think about this list that's being fed in as a group, the constituent would be one item of that group. Make sense? Okay. So constituent parts then even gets broken down even further into individual parts of each of those surfaces. So let's look at what it has given us. The F value is faces, which now there really is no ambiguity between whether or not it's a surface or a boundary or anything like that. It's actually a surface. It's a face. We also have edges or curves. Notice how under params here we have this one. It's for curve. It's the same icon, little swirly, little whirlpool. Edges in this particular case is the same as a curve. And then we have vertices. So yeah, I don't want to go into vertices versus points. For all intents and purposes, right now, vertices are the same as points. Okay, well, we're working in 2D, it's the same. We'll explain more about 3D later. So anyway, we basically have what designers and illustrators refer to as point, line, and plane. Point, line, and plane are your essential building blocks to anything in the three-dimensional world. So now we have 9 locally defined faces, right? But now it's n equals 1, so each particular set is just one item. So if I override this to that, notice how it comes through as each item is in its own set versus a flattened list that reads 0 through 9, or 0 through 8. So I can flatten that and get it to read differently. And now it's going to be indexed 0 to 8. Okay. Similarly, we have the same thing with edges, except the edges are now coming through as packages of 4. And then the vertices are coming through as well as packages of 4. So what questions do you have on that so far? We're going to go through, the next step here is I'm going to show you like visually where it is in space there. And we're going to learn how to isolate particular elements within that ordering system and play around with how you're reading the data. Okay, so what questions do you have about this so far? And I'm going to come around and just double check that at this point we're all on the same page before we move on any further.
So this is applicable only to surfaces?
No. Well,
To general objects?
I'd say, simply put, yes, this is applicable to surfaces. But that's not always the case because surfaces don't always act like just surfaces. Does that make sense?
Okay, and so if you want to analyze all this information and know all the various different points, is that so you can take that, manipulate, find a certain point and then manipulate in a certain way?
Mm-hmm.
So you can insert like another node at that one point, put like a certain, like modify a certain point.
Mm-hmm. Yep, that's why.
So you're basically just zooming in.
Yeah, so what we've done is we've constructed a bunch of panels, and now we've extracted the information that we need to manipulate each of those panels in particular ways. And it could be the same manipulation to all the panels, which is why we have those sets, or we could flatten it and pick one of them out and manipulate just one. So we need these lists and sets in order to determine where and when and how we're modifying each particular element.
Okay.
Make sense?
Yep.
Now, can you explain the use in a practical way?
Sure. Yeah, that's a very good question. And I wonder if it would just be better to show you a larger script, and then you'll kind of understand,
Well,
rather than just explain. I'll try to explain it simply, and if you don't get it, then I'll just pull up a larger script and I'll show you how it fits in. But basically, if you think of it this way, right? So we have faces. Let me do it. Yeah. So basically, with these untrimmed surfaces, if I wanted to rotate them, I would be able to establish. I'd grab these panels, and I could say, and I'll explain how the ordering system works here in a second. But each of these edges has an index number, right? So if I want this to be a louver system, right, like blinds,
okay.
then I would say I want edge 1, 2, 3, right? So every panel I want to grab edge 3, and I want to rotate it around edge 3 30 degrees. So then every single one of these panels is going to fold out 30 degrees and create a blind, like a Venetian blind.
Right.
Does that make sense?
Yeah, it makes sense.
So I don't know if the video got that, but so just to make sure it's on there for you guys, what I was saying is all of the edges have index values based on what you're seeing here, right? So there's edge 1, 2, and 3, and 0, 1, 2, and 3. So I would grab edge 0, 1, 2, actually. 2 is 3. So I'd grab edge 3, which is actually going to be on the top edge of these panels, and fold it out 30 degrees, or use a rotator. And we'll get there. I'll show you that. And so I'm going to show you how to isolate that in the next step. Okay? Yes?
What about when you're when you're gathering information from a surface that is not like a square? Okay, let's say it's circular, or round, or curvy.
Mm-hmm.
How would you go about analyzing that information? Does it still set up a grid for that surface? Or do some grids get cut off because of the shape?
It depends. So there are different ways of establishing a grid on an irregular surface. That's what we would call it, an irregular surface. You can map it to the u and v coordinates, which that's a little different now than your x and y's, right? So we talked about x and y, which relates directly to this. U and v coordinates are based off of I forget the term for it, but basically the outbounds of your geometry, however irregular. So if I have a surface that looks kind of, like a vase, right? Like that. The u and v is going to have the same number of subdivisions wherever it's as close to as close to perpendicular as possible. So if I subdivide this twice in each direction, it's going to look like this. Something like that.
And why is that? Or like the horizontal lines, like you specifically made them at angles?
Yeah. Well, because this one, I'm kind of simulating a 3D one. Like if this was a high point, like a hill, then this would actually be a little bit bulbous, kind of going outward like that. And this one would kind of go in like that. It'll be easier to show you when we actually do it, but you'll see, and you'll begin to understand kind of how it behaves. But what it tries to do is, in a three-dimensional surface, it tries to connect. I'm not even going to be able to. Thank you. I'm not going to be able to just draw it on the board or explain it, but know that it'll be explained once we start doing warped surfaces. Okay. But I don't want to confuse you with UVs yet. Okay. Anyway, so we'll move on.